workshop. So my name is Vigneshwaran, and I'm working under Professor Srinivas Chakravarti, sir, as a PhD student. So Aditya here will also be available in case you have like any doubts or something, and you can put it in the chat box, and he'll be helping you guys along with me. So, as the theme of this presentation, as it mentioned earlier, so it's like how we could able to capture, for example, systems like visual or auditory systems using like a simple convolutional network. So although we say brain is like very complex and complicated system, convolution network on the other hand is like like relatively much simpler, and still we could able to get many trends that is observed in the brain. So some of these examples is what we will be seeing in the session. So to give a brief summary of the entire presentations, like it's actually divided into three phases, and so each phase will be having a particular, uh, like the objective to cover. So the first phase will have like fundamentals, like what are different operations and terminologies that we will keep using. And although it may look a bit, simpler and like much known, so it's always better like the clarity we have. So, so I hope like that phase will help you clear such objectives. And in the second phase, it'll be like more of hands-on, like where we'll train a CNN and visualize feature maps and like some hierarchical feature representations that come along. And then the phase three, where we'll take like a paper from Kell and McDermott lab, where they have shown how CNN, although it's like simple CNN trained on some auditory task, could able to like match the patterns that emerge in the brain. So with this, we'll start. Okay. So now, so any you take any CNN. So the first thing and the very basic thing in a CNN is a filter. So what is a filter? So as the name itself suggests, it's something that like it just binds to some particular feature, and it only let alone that particular feature, and it ignores all other remaining things. So let's take a simple example. Let's take this as some image like grid. And here we have two components like vertical bars and horizontal bars. Suppose what if I want to make a filter that only filters like, for example, vertical lines. So what I would be essentially doing is mathematically I'll be doing something called convolutional operation using a using a thing called filter. So that filter will be a matrix essentially. And in this case, we take some 3 cross 3 matrix. And what we do is we do a convolution operation across this image. So once we do this convolution operation across the image, the resultant output would look something like this. So we can see how the filter has only let go of the vertical lines, and it completely filtered out the horizontal ones. So this is a simple, like edge filter. So now let's take a more complicated example. For example, human faces. So here, like we have two images. So now again, let's try to apply our vertical filter here for both the images. So what we get is something like this. So here we can see, although the image is like quite complicated, it has like many vertical, like, dashes across the image. So we can see how the vertical ones are like more, pronounced. The effect is more pronounced, but whereas the horizontal ones are like kind of left out. So just let's zoom in a bit. So let's take this particular part of the image. So as you can see, the original image, when applied a vertical filter, so we could see the horizontal component are like completely missing. So we can see this particular part of the lip is like gone. But whereas only the vertical components are like left over. So now we can see that in order to, for example, I show this particular image and I ask you to, say like you say whether it's Julia Roberts or not. So you'd be not just using a vertical filter. maybe by using just a vertical filter, in fact, you are like losing information and you couldn't able to identify who is it. So in that case, what we need is we need, for example, in this case, let's also have some horizontal filter. So which is like, some again 3x3 kernel. And again, we apply convolution operation across this input image. But now what we see is we can see the horizontal edges are like more pronounced than the vertical one. And now this may help, like to identify who is this or like, you know, uh, whether you know this person and things like that. So this is like a brief intro of, like how a simple vertical and horizontal filters have some transformation on the input image. So you can see this clearly. So if you want to visualize the kernel itself, so the kernel, as you see, it's a 3x3 matrix. A simple horizontal kernel will look something like this, and vertical kernel looks something like. It's just an example, and there are like you can have infinite number of kernels, and according to your own needs. So that's where convolutional network comes handy. So what convolutional network does is, so it simply learns this matrix, or in other way, it knows what are the values in this matrix, so that it could aid to solve the task in hand. Suppose here the task is to explain whether the given image is like male or female. So the different kernels are trained by convolutional network, so that all these different features could be like learned, and they could be grouped, and finally they could able to say whether the given image is like most probably a man or a woman. Okay, so I hope this particular thing is clear. So now let's go to a neuroscience point of view.
Hello, sir. Sorry for
Yeah.
interrupting. I just joined like 2, 3 minutes late. Can you like quickly recap what you said? The kernel is like a matrix that represents an image.
Yeah, so what it does is you take a kernel. So
Okay.
so which will be like a 3x3 matrix or 2x2 matrix, whatever.
Okay. Okay.
And you do a convolutional operation on an image. Suppose if your kernel is in such a way that it only filters the vertical line. So if you apply a convolution operation on the image using the kernel, you will get only
Mhm.
the vertical edges like this. If suppose it's an
Okay.
horizontal filter, then you would only have the horizontal lines.
Horizontal.
Okay. Cool. So now let's go to the bit more neuroscience specific. So as we know, like suppose a complex task of, for example, identifying a particular person using their face is indeed a very difficult job. So, like we have a clear hierarchy of neurons all the way from retina to, visual cortex. So what happens is like some neurons, so they don't see it as an entire, like recognizing it as a face or like, where this particular bar is moving, in which direction moving in, how fast it's moving. But rather, so a particular neuron, the task is well defined. So the task, for example, this particular neuron will be simply it will fire whenever a vertical edge is shown towards it. So this is where the concept called a tuning response comes. So here, let's see a classic example. Cat is shown some kind of moving bar in the screen, and you show the bar in different orientation, and you record a particular neuron, and you see when at which orientation of the bar the neuron fires maximum. So you can see whenever a bar is perfectly vertical, the neuron's response is maximum. So to show it in a more of a tuning curve characteristics, you can see for different orientation and its firing response. You can see at the vertical, whenever the bar is vertical, it shows the maximum response. So, so in other words, so what the particular neuron does is it simply acts as a kernel. So although we say it as a 3x3 matrix here, like this, the neuron here simply acts like something similar to this. And that's how we can draw an analogy between a convolutional neural network and our visual system in the brain. Okay, so let's move ahead. So now let's see what actually means by convolution operation. So I guess people who know signal processing, they might be like well familiar with this. So you take some part of the image. Although we say image, it's a matrix. So we take a part of the image like 3 cross 3, and you take one more matrix which is which we call as filter kernel, whatever, and you do element wise multiplication. So for example, the first element here multiply with second first element here and so on. And you add all this multiplicate all these products as a single value, and that will be your convolved output. So now you do it for the entire image. So how will we do it? So essentially we have to slide across. So first like the kernel will sit on the first 3 by 3, and then it will move to the next part, and then it'll fully cover the first row, and then it so on to the entire image. To see it more visually. So this is what we actually do. So we take a 3 by 3 kernel and apply across, for example, 4 by 4 image, and we do something called convolution, which I said like element wise multiplication, and finally the sum of all such products, and we put it in the output here. So I hope so far it's clear what is convolution. Now we also have something called bias. So what bias essentially does is this kind of multiplication, what it does is it does some kind of scalar transformation, but not essentially some translative transformation. What I mean by that is, suppose you have y on your left hand side and x on the right hand side, and you want to match each other. So what will we do? Essentially, we'll put y is some a times of x, or a1 times of x, a2 times of x. Although the x scales according to a1, a2, but it will not have a transformative. Like suppose you want to shift it across, x axis or y axis. For that, you need to have some kind of additive term, which will be bias here. So that's what the convolution. So these are the two essential parameters in a convolution network, which is kernel and bias. So both of these will be trained. So all these things we will see in the following sessions. So yeah, why is bias needed? So can someone quickly calculate this and say the answer? Say the resultant 2 by 2 matrix. Anyone? So the input image is 3 by 3, and the kernel of 2 by 2 slides over it. So what will be the output matrix?
90.
Yeah, cool. So it's just a one of 2 by 2, but yeah, good. So I hope everyone is clear so far. And so across this presentation, I have also added like a lot of materials which you can like look after the session. So all these are like really interesting things. Like for example, the video by 3 Blue 1 Brown, he explains very nicely what does this convolution operation actually do and how this transformation look. So
Sir, is
now,
the filter Gaussian filter?
no, it's just some normal matrix. So Gaussian
Okay.
filter will have a Gaussian function along with the convolution. But here it's just a normal multiplication. So,
Okay.
so the Gaussian kernel will look like a Gaussian function. Here, there is no such restriction. It can be any number so far. Okay. So moving on. So we'll quickly introduce these terms, stride, padding, and then what is n-dimensional kernels and things like that. So as the name suggests, stride is it's simply the shift. For example, the number of jumps it has to do to cover the entire image. So the first red one is the first at the time step t. Then when it wants to stride, it has two options, right? It can either jump directly two columns, or it wants to just jump to immediate next. So if it jumps to immediate next, as it's shown in the green square, then it will be a stride one, because it basically jumps one stride, one column. If it's stride two, then it will be like, it'll directly jump this part of the image. So this stride is very important because it shows, it essentially, says like how much of overlap of information you are going to have in the network. So more the stride, it's more faster, but you may also like lose some kind of overlapping information. But very less the stride, you may have like redundant information and you may have like a bigger feature map. So next, moving on to padding. So as again, as the name suggests, it's a very simple concept. Suppose if I say padding equal to 1, what it does is it simply puts a pad across this image. So with value 0, because it's essentially like a frame. And when we want to slide across this input image, it also overlaps with the padded area. So it not be just the input image, but also the padded area. So again, this helps in suppose you want to take only this part of you want to scan each and every corner. If you don't have a padding, what may happen is it may not sit in this exact top right corner, for example. So in that case, if you add a pad, then it can go here and it will take this part also. So yeah, it's a simple concept, but again, it also has like how many overlaps you want, and it depends, and uh, it depends on the task basically. So now, then the third concept that want to see is called n-dimensional filter. So far, all the filters that we had is like 3x3, 2x2, 4x4. But what if their dimension also has one more axis, which is called depth? So why it is necessary is any input image that you see in real world are like a color RGB image. And as we know, the color image have three channels, red, green, and blue. So it's essential to have some kind of depth perception by using the kernels as well. So here we can see input image of 6x6, which is height and width, and three channels. And you want to apply convolution. Now, if you have a simple 2x2, what is the bottleneck is that same 3x3 would be like scanning for all three such channels. But instead, if you have a 3x3 cross 3, which is like three such 3x3 filters, then you can use the red one. So you can use the first filter for red alone and then the second filter for green and blue in such a way that you will have like deferred information for each of these color channels. So that's the only aim that we use these kind of n-dimensional filters. And as we see, it's not necessarily it has to be only three, because just because the input image is three, we can also have like for five number of filters or six filters. So what all they does is like it's just showing a different using same filter instead of all the channel. It's like different filters on different channels. So it's like as simple as that. I hope so far it's clear for everyone. Anyone have any doubt? Like you can.
Hello, sir.
Yeah,
So how the values of filter or kernel is decided?
yeah. So that we will see in the following session. So far, like we just wrote like simply some numbers, and even the vertical filter that we saw, like it's like pre-written. We didn't calculate anything or things like that. It's just like some nine numbers that we put. So in the following session, we'll see how these numbers are evolved and how it will help to solve a particular task. All right. So so just before so this is like a very nice blog by a course in Stanford. Like you can also check out this thing. So they clearly have shown like how convolution operation perform for different filters and different kernels and things like that. Yeah. So now let's see why kernel size is very important. So as the meme itself shows, if your kernel is too big, then what happens is you are like overlooking a particular image. But if your kernel is too small, then what you are essentially doing is like you are, like too much pedantic on a particular like local features, and you may miss a global information. So that should be a right mix. So that's where the kernel design is very important. So before we appreciate why kernel size is important, so we have to know a concept called receptive field. So what is receptive field? So let's take, we have three uh, series of convolution operations being taken place. So let's take the first layer's kernel size is 3 cross 3. And as we know, this 3 cross 3 will give a particular of one value, which is a single value based on convolution. And in the second layer, we again have a 3 by 3 kernel. And this 3 by 3 kernel will give you a single value in the third layer. So now, if someone asks what this particular yellow patch that I'm pointing to is seeing from the input image. So what are the parts in the input image that this particular yellow, like the yellow value has seen? So then you have to essentially calculate something called receptive field. So what it is, it's very simple. So, we know that this particular yellow is seeing this 3 by 3 part of the second convolution. And this 3 by 3 in turn is seeing something like 5 by 5 of the input image. So, then the answer is, so this particular yellow blob is seeing the entire image from, although it's single value. So what it says is like it's a single representation of the entire image. So when we slide across, so it's a different parts of the image. So now the question comes like, should the receptive field be more or the receptive field should be less? So the answer is the receptive field should be more, but it should be a step-by-step increase. So you can't have the entire image seen in the second image. Then what may happen is you are essentially seeing the global image or the global information and you are losing out on the local features. But whereas if your receptive field is like very small, then you are like having a very strong focus on some local feature, and in turn you are losing the global information. So I hope receptive field is clear. So now it's also a very important concept in neuroscience. So as we know, we have like different kinds of neurons all the way from retina to V1, V2, V3, and so on. So some simple cells in LGN, for example, lateral geniculate nucleus, they show some behavior called on-center off-surround receptive field. So what it essentially means is, so for this particular neuron, it will only fire whenever a input hits on the center or the light. Here light, because although we say it as a values in matrix, it's essentially some kind of light that we are seeing. So we can see when the spot hits on the center of the neuron or the cell, the neuron gives a very good firing response. But whereas if the light hits on some of its blind spot per se, or like where the receptive field, it couldn't like, as it's not a receptive field, so the neuron's response is very weak. And as we have like, thousands of neurons, so there will be some neurons which are like off center on surround kind of thing, which is like a complete complement of whatever the on center of surround is. So here the case is whenever the light hits on the periphery, for example in this rim, then only the cell will fire rapidly or to its maximum capacity. But whereas if the light hits on its blind spot or the center, then the neuron simply doesn't respond. So it stays silent. So this is why receptive field is an important concept. I hope so far it's clear.
This
I
receptive
have
field, are you talking about retina?
So it's not just retina, it's all the way from retina to our cortex. So as we see, like, for example, let's take a single cell cannot, for example, a single photoreceptor in retina can't see the entire thing what we are seeing, right? So that particular cell in retina passes a small patch of the view that we see, and that small patch information is passed to the next layers, and what happens is many such small patches are stitched together in somewhere in cortex or like lateral part of the cortex, and essentially they are helping to recognize or like identify what it is. Is so far clear, everyone?
So I think this photoreceptors, I mean, this on and off center, they help to bring more contrast for the borders or lines. So this
Yes.
CNN is all about detecting the borders or edges. So I think that is the analogy you're trying to make.
Uh, okay, so it's not as simple as that. So both are uh, a single neuron is like a very specific characteristic. So this particular neuron is will just fire whenever the light hits its center, or like or the other case. But a CNN on the other case is like, again, it has a very specific property. For example, as we saw, whenever there is a vertical bar is shown in its receptive field, then only it will fire. So it's just an analogy between both the networks. I hope it's
Uh,
clear. Yeah.
yeah, I just wanted to ask that do we use stride padding and receptive field in the same model?
Yes. So all these things that we saw, like for example, the number of filters that we want to have, and the level of padding that we want to have, and the stride that we want to have, all these things are like configured in our convolutional network. And all these three, although people overlook it, they have an important role in like in your performance metrics. So they should be chosen carefully.
Okay, so what is the order of like going through that? Is there any kind of order like first stride, then padding?
Yeah. So yes. So that we will be seeing when I show, for example, a Python code, how we configure all these things. But so far,
Okay,
the thing is like, is the like what does it mean if we say stride or like padding? So the objective is like only so far with that.
okay, and just last question.
Mm.
Through that, we are representing bunch of neurons, not a single neuron. Uh, is it right, or do you
Yeah.
get my question?
So
Yeah.
you are asking in brain or in the convolution?
Yeah, matlab, through convolution, I'm just trying to understand, is it for the network, right? For the whole, I mean, the bunch of neurons, the particular brain region that we are interested, or is it for a particular neuron that we
Okay.
are trying to do in a model?
Okay, so we use such convolutional network to explain the visual system per se. And when we say what is the particular neuron in a convolutional network, it's essentially like some abstract unit. So we can't map a single neuron in convolution and like a real neuron in the brain. So I think that's where this rate coded concept comes. So here the single convolutional network's neuron is essentially some kind of rate coded neuron in the real brain. It's just a modeling. So we can't have a direct one-to-one connection with it.
Okay, okay. Thank you.
Yeah.
Can you just see if my understanding is correct? Like, so you mean to say that like the deeper layers of, I mean, neurons in the visual network, like just like in CNN, they have a corresponding receptive field in the retina, right? Just like,
Yes.
and so some neurons get activated when the center part of that receptive field is stimulated, and some neurons get activated when the periphery, like exact opposite. That's the
Yeah.
understanding. Yeah.
Yes, correct. So the also the idea, just to add to your point, so the receptive field of a single neuron keeps increasing as we go deeper and deeper. So if I add one more layer 4, so that will be seeing even more huge part of the input image. Why? Because as you can see, again the 3 by 3 kernel will have mapped to some 9 by 9, and that 9 by 9 will have so similar such scaling.
Okay. Okay.
Yeah. Uh, okay. Okay, then I'll just say what is although I planned what phase two. Okay, so we'll again stop by some like a few three concepts here. So the first thing is called pooling, and why it is important in a convolutional neural network. And then we'll also see a brief intro about backprop and autograd. Although you might have heard about it, many times. I hope that it will just refine your understanding by this presentation. So now, quickly going on to pooling. So as the name itself suggests, it's a very simple operation. So let's take a input image. It looks something like this. It's 4x4 input image. And suppose someone says do 2x2 max pooling with stride 2. So what they say is you overlap 2 by 2 on the first part, so which is like the top left corner, and now the pooling operation is max pooling. So which means you simply have to select the maximum value in this 2 by 2 thing, which will be 12. And then now the stride is 2. So what it means, then we have to skip 2 columns, like we have to jump. So we'll jump 1 and 2, and we take this 2 by 2, and again we calculate which is the maximum among these 4 values, which will be 7, and similarly do for other 2 parts. So this will give 2 by 2 as the resultant output. And if someone says what is average pooling, it's very simple. You have to add and calculate divided by the total number of elements, which will give you the average pooling. So why pooling is important? So pooling is, first of all, important because it reduces the dimension very rapidly. As you can see, the entire 4x4 has just become 2x2. And we assume this 2x2 is a good representation of our 4x4. So we essentially, it's like among the group, you choose one candidate who will be a good representation of that pool. So that's what happens here. So the main reason is just for dimensionality reduction, and thereby your number of parameters in the network will be much lesser. So, and to say it in a more, so one more reason why pooling is important is, again, when we say reduction in dimension, it also aids us in better performance because we are letting go of some redundant information. So we basically don't need that redundant information, and we only choose one candidate among that particular pool who would be like, like would be way more sufficient for whatever the task is. So now, can anyone say this max pooling answer for 2x2 with stride 2? Anyone, please, quickly?
100, 184, 12, 45. That's for
Cool.
max pooling.
Yeah, cool. Yeah, that's fine. So I hope it's clear so far. If not, please don't hesitate to unmute and ask. Okay. So now,
So let me
yeah.
ask this convolution and pooling, both we are doing for feature reduction, right?
Yes. So in convolution, we have some kernel that we multiply with, but in pooling, we don't do any such thing. So it's a non-parameterized operation, but whereas in convolution, you have some parameter, and that parameter will keep changing to improve your performance.
Okay.
Cool. Anyone? Anyone have anything? Okay. So now let's move. So I purposefully added this this section because it will be helpful because we keep saying why PyTorch, TensorFlow, and like, without even knowing, like we do import Torch, import TensorFlow, SDF. But why even we need these libraries and why they are like so popular? So I hope this particular section will help you with that. So now let's take, so now let's go bit theoretical. Let's take that left hand side is y, which will be like your output, and right hand side is x. As for any learning task, we have to match this y to some desired, like y desired, which will be like yd. And the only thing that you have in hand that you can, like a knob that you can change so that your y will be closer to yd is our w. That's why it's called parameter. So you can change this w in different ways so that your y and yd are closer to each other. So to say how good you are doing, you have to have some kind of objective function, which we call loss here. So essentially the objective function here should be minimized. So lesser the objective function, which means the better you are doing. So now the question arises is how can you change this W so that you could essentially achieve this target? So that's where backprop comes. So what it calculates is it calculates something called like how much should I change W so that my loss will change. So now the question comes here is we know that L, in order to L as a function of like some output and thing W, you have some many parameters because Wx is a function of I mean y is a function of x, and this y itself is a function of loss. So you have to literally propagate your like loss to two levels. First to the level of y and to the level of w. So then what we have to do? Then we have to calculate simply change in loss with respect to change in y, and then change in y with respect to change in w. If we can calculate that, then we will calculate this change in L with respect to change in W. And we can simply update this W and we could get a better and better estimate. And the theoretically you can't update the weight tab just based on this value, but rather a small scalar times that value gradient. So the scalar is simply a learning rate, and it should be small so that like your uh, the journey towards the better and better estimate is smoother, and you don't jump across or like you don't go so too slow. So that right mix of exploration exploitation is math is taken care by this alpha, which is your learning rate. So now all this theoretical stuff is fine, but why Torch is famous or like why TensorFlow is famous is, so now let's assume you have like some 10 layers of neurons and you want to backpropagate your loss all the way to the input layer. Now, like the situation becomes bit difficult because you have to calculate the differentiation of each, like each layer, and each layer will have some kind of activation function. And you have to calculate change in activation with respect to change in input. So essentially, you have to differentiate the activation function with respect to the input. And then so on to, like n steps to go to change your weights in the input layer. So in order to avoid that, that's what these libraries does. It's called AutoGrad. So let's take so so in all this tutorial, we'll be using Torch because it's a bit simpler than TensorFlow. So let's take a simple x value which is from -4 to 4, and have a function which is like a function of t. So it's like t square plus 3t plus 5, some nonlinear function. So now you have to find the differentiation of f with respect to t. So how will you do? So if someone asks, we will be like, analytically differentiate it and say this is the function. But it might get, as I said, it may get tedious if you have like, many layers and the functions are like too, uh, complicated. So that's where Torch comes. So if you simply calculate f dot some backward, which is like a function to compute its gradient, it will store the gradient in t dot grad. So if you want to plot it and see, so the blue line is our input function, like the function, which is t square plus 3t plus 5. And when I call like t dot grad, what it becomes is it simply shows the plot of the differentiation of the f. We can see. So we didn't do any, like x squares is like 2x. We did nothing. We simply called dot grad and it simply did the differentiation for us. Now let's take another example. Suppose the input, like the function is sin x, and you want to calculate the differentiation of sin x. Again, you simply call x dot grad and you plot it. It becomes cos x. As we know, sin x differentiation is cos x. So this is why Torch and TensorFlow are famous. So they literally do something called AutoGrad. So which is like it has something called a graph. So whatever the operation that we do, it simply converts into a graph, and it stores and it maintains all the operations that we do, and it simply differentiates backward so that we would calculate the change in loss with respect to change in parameter. So here, for example, W. So all the way this J is back, the change in respect to J is back propagated to change in with respect to W. So this, it stores as a graph. So this is what as the feature is called autograph. Anyone have any doubt? Okay. So yeah, so again, so this video is like really a cool one, like where they show how back propagation, what actually happens in back propagation, and they show with nice visualizations. Um, so with this, maybe we'll take some 2 to 3 minute break, 2 to 3 minutes break, and then we will move on to like bit more of how to visualize, for example, MNIST data and how the like the intermediate convolutional layer works, and like some few of the people's question where they asked how to do padding straight and like how different layers should be added. So all these things we'll be seeing the next session. So if you have any doubt, like we can also create breakout room and discuss. So now time is 2:42. Maybe at 2:45 we will again start. Is it fine for everyone?
Yeah, okay, sir.
Yeah. Okay, all right. So now I hope all of you have the collab notebook, the same collab notebook that I'm sharing, screen sharing. So I would recommend all of you guys to open that and create your own copy, because I guess you'd be only having view access to it. So you can create, make a copy and then run these codes, whatever like we'll be going through. Uh, okay. So now, um, so far it's all story there is edge detector and then some like horizontal line edge detector, some slant edge detector, and all this. Now let's see whether some of these things are like automatically evolved when we try, for example, train a simple convolutional neural network on a very basic task, which is like MNIST dataset. I hope many of you know what's MNIST dataset, which is a simple handwritten digit recognition. So yeah, something like this. Yeah, so there'll be like 0 to 9 digits, and we have to simply classify what the particular digit is. So now, so what I will be doing is like I'll explain all this code that we have. Although it looks like not very big, but it's like a very straightforward one, and I hope like it'll be easily followed by everyone. So now, so far, like we saw why torch is important and why there is a big
Hello.
buzz around it. Yeah.
Uh, Sir, how this PyTorch is different from TensorFlow? Means how it is
So
useful?
functionality wise, there is no difference. Both of them do the same thing, but it's just TensorFlow is from Google and PyTorch is from Meta, and there is no much difference. So obviously there'll be change in syntax in both of them, and we use Torch, but not necessarily like one is like advantage towards other or something like that. You can use any of this. Okay, so now, so as any Python script, like we have to import the necessary files. So Torch we need, and then inside Torch we also need to use something called NN module, and this NN module is where we'll have like like entourage of different networks that we can readily use to our network, and like use it in a very systematic way. And torch.optim has something is for something called optimizer. As you know, optimizer is necessary. Why? Because we have to either maximize or minimize our objective function. So in our case, it's a loss is the objective function, so we have to minimize it. So the optimization becomes like minimization optimization problem. And then to download the data set, we need something called Torch Vision, so which will provide us with a MNIST. And we also need some data loader things to handle the data. And as usual, like other standard matplotlib for plot, numpy for array operations, and math for some mathematical operations. So any Torch code will have a particular thing called like network class. So people who are familiar with Python and then things like object-oriented programming. So what essentially it does is it the torch gives you some different classes that you can readily inherit in your network and use it in a very like non complicated way. So NN dot module is itself a class. So in Python, we know that if you put something like that, it's an inheritance. So which is our net class, this is ours, which inherits the module class, which is PyTorch. And because of this, we could readily use its autograd capability. Then inside our network, we essentially have two important functions. We can have hundreds of functions, but these two are necessary. As you know, first is a constructor. I hope people like know what is constructor, which simply, as the name says, it simply initiates the necessary attributes and functions of the class. So here our attributes are different convolutional layers that we want for our particular task. So what we do is we call it at instantiate, and self.con means self is to say that it belongs to this particular class. So when we put self.con, it is like this self.con belongs to the class net. So we put the first, so we instantiate the first convolutional network. And the syntax for this is, so let's in fact see the official thing. So that will be, so we use convolutional 2D. So this is the syntax. So as the documentation says, first we have to put the input channels. That is the images, number of channels it has. So our MNIST data is a grayscale image, means like black and white kind of thing. So we don't have a red, green, and blue. If it's a RGB, then the input channel will be 3. And output channel is the number of kernels that we want. As we saw in the n-dimensional kernel, we can have 10 number of kernels or even one, like whatever. So this out channel defines that, and the kernel size. So all these things that we kept saying, like kernel size and then stride padding, all these things come here. So now let's go back here. So here we are saying the input channel is 1. Like I said, it's a grayscale, so 1. And we are saying we need 32 filters. Like bit too much, but just for the case. And then 3. What is 3? So 3 is kernel size. So we are saying 3 cross 3. As we are setting 3 cross 3 as the kernel size. Now someone asked how do you like say what are the values of the kernel. So here the network starts randomly. So it has some random numbers as the random like the initialization, like some -1 to 1 or like -0.1 to 0.1. And then the values keep evolving based on your optimizer so that you can do the particular task. So then we have convolution 1, convolution 2, and convolution 3. And we can see the output channels is the input channel for the second convolution. Why? Because after first convolution, we'll have this many channels as the output, and that many channels will be the input channel for the second convolution. Simple. And then it becomes 64 and 128. In all the three, we only use 3 cross 3, and we have padding as 1. So we know padding as 1 means it simply adds 1 row and 1 column, like it puts a frame around the input image with zeros. And we use the max pooling 2D. So again, we saw what is max pooling, and here the size is 2 cross 2. So very straightforward. And then so far, after all this operation, it will be in, like the dimension of width, comma, height, comma, number of channels. But we don't want to have, like 3D, like, feature maps. So instead of that, what we want is we simply flatten it out and pass it to some normal, like MLP like thing. I hope MLP is like sir, professor taught in the morning session. So like we have simple MLP, and at last the output of the MLP will be at 10 neurons. So these 10 neurons represent which of the class that we want to, that you are saying, what the network is saying as the likely class of the given input image. So now this is the first part of the network, and the second part is called forward. Again, this is very important. Why? Because it only says how you are constructing this particular graph. So you get some input X, and what are the parameters that you want to multiply with or add with, whatever the differentiable operation that you want to do to get the final output. So this you can define it in the forward. And so as I say in the graph, the first input node will be the input. Input will be input. And what happens is we pass it to the first convolution layer, and the output of the first convolution layer will be we'll be applying ReLU after it. I hope ReLU and all those activation functions are known. If you have any doubt, please don't hesitate to unmute and ask, because it's very simple, and it's like uh, I'm pretty sure by the end of the session, you guys should be like, like well versed and like have a very strong conceptual clarity on what convolution and everything. And then on that output, we apply pooling. So again, someone asked what is the order? Is there any specific order that you have to do convolution, pooling, things like that? So the thumb rule here is you apply convolution and you do pooling, so that the redundant information that happens that are present after convolution will be pooled in such a way that dimensionality is reduced for the next convolution operation. So we can see that the pooling will essentially make the dimension as half because it's a 2 by 2 pooling and gives to x1, and that will be the x1. And again, you do the same thing and you get x2, and again, you do the same thing with convolution 3 for x3. Now, after you do all these things, you simply flatten it. Like you have you have the output x3 will be in a cuboid shape, which you simply flatten it, make it linear, which is what this does. X3 dot view as -1. -1 is simply a flattening, uh, like a flattening operation. And after you do, you get something called x flat, and you pass it to some two linear layers, and you get output. So output will be some 10 values, and whichever neuron's value is maximum, so that's what network is saying the particular digit is. Suppose when I show image of 3, then the 0, 1, 2, 3, the fourth neuron should have the maximum value among the with respect to other 9 neurons. So if it's not, then our loss will be higher. Then we update the weights so that loss next time will be lesser than the loss the current time, and your predictions become more accurate and accurate. So I took more time to explain this torch thing because this is very common template. Even if you want to use transformers or like RNNs, even whatever like advanced ResNet, UNet, whatever you want to use, this is the common template that you should be well versed with. Then so now we can go a bit faster. Like you have train function, and you simply know what is batch, because you can't give the entire some 20,000 images directly to the network, because in the background there is a RAM which has a simple fixed memory. So you can't load like 10 GB of data, something like that. So you have to divide it into batches and give one by one. And so you give you give the data to the model and you get output, and then you calculate loss. So here it's cross entropy loss. So again, I hope people know what's cross entropy loss. It simply says how the two distributions are similar. So if the two distributions are very similar, then the loss will be very less. If the distributions are very dissimilar, then the loss will be high. So it calculates loss. So our objective here is to reduce the loss. So what we do, so here comes the magic function for all this torch bus, which is loss dot backward. And now it simply attaches the gradient for all our Ws. So here it's like all our kernels will have values attached to them, which is change in loss with respect to their values, which will be like del L by del W. And then optimizer.step. The optimizer.step will do this thing basically, this particular thing. So after we do this, the next time or the next epoch should have a lesser loss theoretically. And we keep running it for many iterations until we are, satisfied with our network's performance and, things like that. And you can also test things. So now, can you guys all try to run this code? And for example, can you see this output? Like you just run for 2 epochs and you see like first loss is like 2.3, and then the next epoch it rapidly reduced to 0.08.
Hello?
If any, yeah,
Hello?
yeah.
Um, yeah, sure, I have a small doubt because we are doing with a very large data set, right? So whether we are trying with all the bunches of data or some randomization is taken place for selection of the bunches.
Yeah. So here we use the entire data, but we divide them into batches. So a network will be trained one at a time for that batch alone. So because we have limited RAM capacity, so we can't load the entire data into a network.
After that, after running with all the batches, the average of this one is taken as condition or
Yes, yes. Average of that is like the So this loss is an average of all such batches, for example.
Okay. So average is considered as the correct predictor.
Yes. Yeah.
Oh, so we are running all the batches, right?
Yeah. So if you
Okay.
run all the batches, at the end of that, it's called one epoch.
Okay.
Yeah.
Okay. Thank you.
Yeah. So I hope at least everyone made a copy of this thing and then running in their own accounts. If is anyone having any difficulty, like their loss is not reducing or like running into some error? Okay. So now let the network train. I hope it started training. So now let's see after two epochs, obviously we started with some random kernels, like 3 by 3 kernels of like 32 such kernels, 64 such kernels and things like that. But after, like repeated updates, let's see how the kernels look like. So we can see the first convolutional layers, look something like this. And the second convolutional kernels, no. So although there are 64, like we are only seeing, 36 of them. And then third looks something like this. So now this is where the hierarchy emerges. Now let's take two input images, which is like digit 3 and digit 8, and let's give them to our network separately. So after the first convolution operation, we can see how the output looks like. So as we know, like output is also called feature map. So we can see the feature map, how the feature maps look like. So as we number of feature maps will be equal to the number of kernels. So in the first we had, I guess, 16, if I'm not wrong. We had, 32 we had. So we are only like plotting like first 8 or something like that. And you can see, so it's so this feature map's obviously different from 8, but you can see a very uncanny similarity between our edge detector as shown here in our Julia Roberts Ronaldo picture. You can see, so so you can see it's very similar to this representation here. It's basically like showing the entire, you know, it's just showing the image, but some, for example, horizontal lines are like more protruded. For example, you can see here, it's like more, it's like more like horizontal filter. You can see like, and the vertical are like not that much activated. And you can see here like a clear slant line. It only filters out like particular slant line, and all other thing it completely ignored. Things like that.
So these
Now,
feature maps are actually weights of the later layers of filter, right?
no, this is the output.
Output. Okay, okay. Uh-huh.
So feature map means it's an output. Feature maps and output are same. So although we started out all random, we can see, although, and it has nothing to do with any neuroscience or like we didn't do any hand holding, and we can see all similar such patterns automatically emerge. Now let's go to the second layer. Now things, like it becomes like a bit more complicated for us because we don't know, still even in neuroscience we don't know how complex cells, behaves, and we have not completely decoded it. So again here we can see like many such simple cells are combined to have some kind of complex cells, like similar to complex cell output even in the convolution network. You can see like how, like, I mean, we don't know like what is this like, but it's a very complicated some feature map. And even for this, so someone say why the second layer is like more like, very hard to understand than the first layer based on whatever like we learned.
Receptive field?
Yeah, nice. Okay, because Here, this particular patch in the feature map, it's only seeing like a small window. So it could, like the feature map is like pretty understandable. You can see it's like 8 and things. But now, this particular patch in the second convolution is not just a simple part in the image, but rather a mix of many such feature one's response. So going back, I want you guys to understand this because this is like the whole crux of whatever artificial neural network neuroscience thing. So here this feature map we could able to understand easily because it simply sees the direct image itself and it could match. But here we don't know what it's because it's a combination of many such simple cells or like level layer one features are combined as the some representative blob. So then it becomes like no longer a simple representation. All right. So now let's go here. Now, if the second layer itself is like more complex, then obviously we know third layer is like, it's like full, not so easily interpretable. And also, as we know, like if you do keep doing convolution and pooling, the dimension also reduces. And you can see how this dimension is like much larger than this dimension. And in literally in layer 3, our feature map dimension is like just 3 cross 3. So this is again a property of convolution network, like where the feature map should keep reducing, but the number of feature maps should increase. So this again like a like a theoretical, not a theoretical thing. It's like an empirical thing where the idea is you have small patches in the layer 3, but many such patches, so that they will help you in classify. For example, it's 8 or 3 like that. For example, you can see for this particular channel, for image 3, it literally didn't say it literally like it went full silent. But for 8, like it showed some particular thing. So now there is this emergence of things called class specific or class sensitive neurons. So here, this particular neuron might fire whatever the image might be. It doesn't know whether it's 3 or 8 or anything. But here it becomes very class specific. So you show 4, 5, 6, this particular neuron may not fire at all. But when you show 8, then only it fires, irrespective of what the shape is. Even if the 8 is slant over left to right, or like it's completely like two zeros, whatever it is, this particular neuron will fire. Why? Because it's a very class specific neuron. So this is why the class specificity is happening right before the output. And the simple feature filtering happens in the starting of the network. I hope you guys can appreciate this emergence of hierarchy. And anyone have any doubts like how this happens? All right. So now, okay. So now, were everyone able to run and get the exact features? Did anyone get like,
Trial.
yeah. Yes,
Hello?
please.
Yeah, I got a different value for epoch to 0.9 or something.
Trial.
Okay. So why do you think it's different?
0.9739.
Trial.
Yeah, so can anyone say why that is like different in loss value for him and the loss value here is different? Anyone?
More epoch training.
Yeah, more epoch is fine, but why that is different? For example, I get loss like epoch 2 loss as 0.08, but like I think Abdul got like different 0.9 or something.
0.097393 to be
Yeah,
exact.
so why
Different
is it?
bunch. Different bunch.
Weights are initiated
Input
differently.
is
Yeah, good. So the weights are randomly initialized. So my initial weights will not be same to Abdul's or like Harsha's. So why? Because the objective is you start wherever in the topology, but after some 10 epochs or 5 epochs, we all want to go and settle in some kind of minima. And that minima should be good enough so that whatever the image that we show, it could able to perform very similar to each one of us. Initially, it may be like all random, but we should all like go and settle in some particular minima where that minima is good enough to solve the particular task. So that's why each one of you might have like different laws and like things like that. I hope that's fine. So in fact, that's why this kind of it's called like stochastic gradients, because you take, like, again, someone said like batches are different. Again, that's also one of the reasons. So different batches. So for me, batch one might be different for some others batch one. So all these behaviors, although they are like random, but our ultimately we should all settle in the local minima. Uh, Actually, minima. Local minima is also not a very good thing, but some minima. Yeah. Uh, Anyone got like can anyone share and show like and say like some edge detectors in the first feature map? Like for example, here I show like this like proper horizontal filter. Can anyone uh share and say like their own whatever they found features is? Or at least everyone got these plots? Anyone did not get, or like they ran into any error? Okay. So, all right, then now let's move to like bit more neuroscience specific. So here, I think someone chat. Okay, cool. That's nice. So now let's go bit in our neuroscience part. So now we get input from retina, and retina passes. It's actually, in fact, the term relay is used because it literally relays the signal to like LGN, and then LGN passes to V1. So V1 is like primary visual cortex. And after V1, it goes to V2. And then, so there is this like two pathways tail, which is called VAR pathway and WAT pathway, like dorsal pathway and ventral pathway. As the name suggests, WAT pathway is like V2 directly projects to V4 region, and then it projects to inferotemporal cortex. So this pathway is used to identify what the particular object is. That's why it's called WAT pathway. And whereas the V2 projects to V3 and then MT is like middle temporal region, and then it goes to parietal cortex. So all these pathway, the other pathway is necessary for VAR. So these what are like, like object recognition, simple like horizontal, vertical, and then like what color it is and things like that. But whereas in the VAR pathway, it's more like, what direction it moves. In fact, MT is a region where if someone have some like injured in MT, they may have things like, so they have a problem in visualizing kinetic uh, things like, for example, they may not see a smooth, for example, a car passing by the road. They will see it as like, first they see it somewhere there, and then next instant they see it somewhere right in front of them. They won't be able to perceive it as a smooth motion. And things like this happen when this like VAR pathway is injured. So now, like in neuroscience, this particular hierarchy is like well studied. Now so to see this, let's say you see some image like this, rectangle image. So in the initial layers, they are like simple cells. So it's like they simply fire whenever their own, like the feature affinity is present. If this particular neuron is like, fires whenever this horizontal bar is shown. So it simply fires. And for example, this guy will fire whenever, like vertical things like that. And all these simple cells in the initial layers are combined. So here we can see they do some kind of max pooling kind of thing. And where the other neurons are obviously not, we responded as much as vertical here. So obviously this guy is going to win because he's going to have the maximum response. And combination of many such, simple cells response will have more complicated things. Like for example, this. Now it's a proper, like a transformation, and it gets more and more complicated as we go. And finally, we could say, like this is a rectangle, or it's a circle, or it's a, whatever star. So although it all this different, like millions of neurons are like learn together to fire for one or identify a particular square. So very similar thing we are also seeing in like not so complicated convolution network. So that's where like these kind of tools are like very important to understand different systems in the brain. So now some examples. So this is
Sir,
yeah,
sorry to interrupt. I'd like to clarify one thing.
yeah,
Like, I get it that what you said, what you showed just the last part, the simple cells, right?
yeah.
So that's what we are basically getting in the above level three, right? Something like that, like very abstract or like what to say, deep level representation of something that we can't fully understand until we zoom out a little bit, right?
No. So what I'm saying is this kind
Mm-hmm.
of many such simple cells are combined
Mm-hmm.
hierarchically
Mm-hmm.
that you see, for example, somewhere here that you
Mm-hmm.
don't know, you can't extract, for example, there was a vertical edge from this. This
Mm.
representation is simple, but you take our thing.
Yeah,
Can you
yeah,
say that why this particular blob is there? So can you say whenever I have a horizontal line, I'll get this neuron fire? No, you can't say that.
no.
But rather, I can say whenever a class 8 is shown, this neuron will fire.
Okay,
So
fine,
then
fine.
what it becomes, it no longer a simple feature extractor, but rather a class specific neuron.
Okay, fine, fine. It fires whenever it encounters something like that.
Yes, correct.
Okay, thank you. Sorry for
Cool.
that.
Yeah, no problem. And please be free, like you can, I think we have time. So yeah, so if you have any questions, like, so now let's see something called LayNet. So all this MNIST things was like shown by uh, like a very famous person in deep learning. It's called Jan LeCun. So he trained this kind of handwritten digit recognition, and he did like he also generated some weird samples like this. For example, this is two, but it's like no one writes two like this. Now, can our network, recognize this as two instead of saying it's like zero, for example? And he showed like it could able to, like recognize it as two. So that's where the class specificity. All this receptive field, kernel, like what's the kernel says, all these things sit together so that we don't get lost in, like local feature. For example, if I very focus, I'm not saying this is zero, where rather I'm saying it as two. So I have the global picture as well, but also some local information. And it could able to say it as two. And similarly, like many example, like, three, for example. And he showed like how network can identify, although like they look very different from the data that we trained with. And you guys can check this website. It's like very cool. And then now someone wrote, so suppose if I say like this neuron is class 8 neuron, and like for example some other, this is like class 3 neuron. So then can I say of all the persons that I have seen, like in real life or in any movies or anywhere, so I will have a particular neuron of them. And then he went on and then sorry, he goes on and says like, so if that is the case, then can I say like there is a particular neuron in my brain which is like Jennifer Aniston neuron, and it will only fire whenever I see Jennifer Aniston, for example. And so he used and then he showed like a simple using simple experiment, like that, for example, that particular neuron fires like more rapidly for whenever we show particular face, like in this case, like Jennifer Aniston. For all other cases, it didn't show. Even Jennifer Aniston with like, someone like Brad Pitt or someone like, it didn't fire as much as like a single Jennifer Aniston film. So, so yeah, so we still don't know how, like, higher level neurons encode, for example, face, things like that. But this is like one theoretical thing like people are, seeing. And there's also a very interesting blog by Andrej Karpathy. Like you guys can also check out this. And he so he basically says how our like different self images and you train on convolution. So what actually convolution sees? Like how we say like first layer only sees like edge, and then last layer like finds like it's this is person A, person B. So he like shows it in a nice visualization. So you guys can check that as also. And also this article is like again like very interesting. So he shows like how retinal cells response, like photoreceptor response for different natural scenes and things like that. So yeah, so with this, I think we'll take a break. So since we have like almost 1 hour left, so we may take a 10 minutes break, if that's fine with everyone. We'll meet at 3:35. And in between, if any of you have like any doubts or like you have any problem with the code, like you can ping in the chat, like we can discuss about it. Cool. Let's meet at 3:35 then.
Hi, Vigneshwar.
Yeah. Hi.
There's a question in the chat. So do you want to answer it?
Yeah. I'll just give me a minute, okay? I'll just. Uh, Hi everyone. So I'm just okay. So although not very different, but I wanted to know whether the Renaissance okay. So Prashantsa Tripati. Okay. So I'll just show. Oops. It's my screen. I hope my screen is visible. So now to answer the first question, whether randomization is a problem. So let's take an example here. Yeah, something like this. Yeah. So now I hope this thing is clear. Let me open the image also. So now let's take this axis is our J. So J here is the optimization function or the cost function. So not optimization, it's a cost function. And the parameter like the dimension here are the weight, like theta 0, theta 1 are like a W1, W2 and things like that. So we have to evolve the model in this space such a way that you get maximum, accuracy or like things like that. So now to your question whether randomization is a problem is actually not. So here randomization will be our friend. Why? Because we don't know this topology. So if at all we know this topology, then life would have been much easier. Someone asked like, I'm thirsty, then the optimization is drink water. So that topology is very clear. But when we say, for example, like train handwritten digit or like much more complicated thing, we don't know the actual theta 0 and theta 1 to get maximum of j theta 1. So in that case, that's why randomization is a very powerful tool, because every time it spawns our model in different regions in the space, and it helps to move along the gradient. So here there is a gradient, right? So we are literally moving along the gradient. So when I say gradient here, it's obviously our del j by del theta 0 or del j by del theta 1. So we have to keep, like maximizing, go in the direction of that gradient and reach our maxima or minima. And we know from our math that maxima or minima where our gradient will be close to 0. So here in our network stage, if our del L by del W is closer to 0, which means, like you came to some minima or maxima, and like you have achieved your goal effectively. But that minima or maxima, is it good, or is there some other better minima or maxima exist, but we like struck in some suboptimal minima or maxima? That is a different thing. For example, here we can see this peak might be better than this peak, but we came and struck here. So maybe next time when you start, you may go and like be there. So how can you go and be there? That's where randomization helps. Like, because it's not like every time you end up here. Maybe some other spawning of your model will help you to reach some better minima or maximum. Is that does that answer your question?
Yes, yes. Thank you so much.
Yeah. So here randomization is actually helping us. And although people say like I'm getting different result and all those things, but it's actually good only. That's the other questions.
Okay,
Okay.
thank you.
Yeah. Um, you can fix
Yes.
so one way of, so you can't be like too random, then like you are going like too like unpredictably. So you can, one way is like by setting seed, like someone said. So that's a good way. Um, yeah, so I think that one, let's say once in this multiple iterations, I get a very good result, an optimal one, and other runs I get a suboptimal one. Good fixing the random. Yeah, so exactly. So this is where, so I hope my screen is visible. Aditya, my screen is visible, right?
Yeah, your screen is visible.
Yeah, okay, good. Thanks. So, Hood fixing the random seeds ensure. Yeah, so this is like again the crux of the problem. So if you keep too random, then what happens is like you may have like different result different time. But if you have like very less random, you are like not being so every time you spawn your model in some very small random space. So that also is not good. So again, you have to have a mix of both these things. So this is like a classical instance of exploration exploitation problem. So one example is like suppose you go and eat in a restaurant and you really like the food and you say like, oh, why I have to even look for a new restaurant? I mean, I like the food here, I'll have it forever. But then you may go to some new restaurant which you don't know whether it's good or not, but you may have a more rewarding experience there or like like not so rewarding experience. So exploration is important because you may not stuck in local minima or maxima, but not too much randomization is also not good. Then I think if the model is trained for switching among them, it will converge this. Yeah, correct. So if in the ideal case, however you start from, if there is a one good minima, then ideally or theoretically, all the models should converge into that particular minima or maximum. So yeah, that is true. I was wondering how does completion connects to the link. Okay, so we'll yeah, true. So yes, this is the ultimate thing. Then cool outputs from convention. Yeah, okay. So Atya's answering that. So kind of like mapping the alias. Yeah, so I'll also just show some. Let's go to that CS 231. Yes. So to the person who asked like how it's mapping to this, so this is what literally happens. So you have some 3 by 3, you simply linearize it, so it becomes 9 by 9. Then it's like a normal neural network. So each of this is like projected to some neuron using all to all weights. Suppose here it's 9 and here it's like 4, then obviously the weight matrix is going to be 9 cross 4 so that it's all to all connected. And then it projects to the output, how many ever layers, and last will be the output neuron. And the output neuron, each neuron will say, hey, I'm sure that this is 0 for like this much confidence. I know this for 1. This guy will say, I know this is 1 for this much confidence. This guy will say, like, I know it's 2 for this one. The one who is like very confident is the winner here. And that is the network's prediction. And in the actual ground truth, where your desired output should be like, except that desired neuron, all others should be silent. But that will not be the case. So how do you do it? Then you calculate loss from these two distributions. One is desired and the network predictor. And you make the network to move closer and closer to the desired thing. So that's how it works. Yeah, so again, it's like n-dimensional filter. So yeah, I hope we saw all these things and everyone is clear. So now let's move to our, I hope that's it, right? Yes, fine. Yeah, so now let's see the last part of the session. So here, so far, all we saw is like auditory, sorry, we saw visual system and like how all these things work and things like that. But in auditory, the story is very similar. But again, it's like here the input is not an image, but a sound. So now, so this is the paper that we will be trying to, analyze and see the code for it and things like that. So before moving, how we actually know how we can recognize sound? It's basically by in the input layer how there is retina in the eye. So here we have cochlea. So cochlea is like you can see like it vibrates. So it has like hairs and it vibrates whenever a particular frequency is like given as the input. So there'll be like many, like cells or hair, and the particular cell will show maximum response whenever its desired frequency is shown. Suppose input auditory of 100 hertz is given as input, then there'll be a particular, cell in cochlea that it will vibrate maximum than all other things. So that's how we know that it's a 50 hertz or like 25 hertz or whatever it is. So now what is the function of cochlea is, it basically makes something called cochleogram. And this cochleogram is the input to the further layers of the brain, like, next levels of the auditory cortex. So what is cochleogram? So before that, I guess you guys know what is frequency, time, and then all these things. So now let's take a input signal, input audio that you hear it's something like this. Then what cochlea does is, it computes a spectrogram kind of function, which is like your y-axis will be something like a frequency, and your x-axis will be the time. So this image is further passed to the next layers, and finally you say whether you heard, for example, your name or like someone's name and things like that. So now let's create cochleogram or like spectrogram ourselves. So cochleogram and spectrogram, the difference is spectrogram is like a pure mathematical thing, like, like you say for 20 hertz, it's that 20 hertz will be there. But cochleogram is, in the other thing, it's like more of subjective thing. For example, if you are like, we know that human auditory works in the range of 20 to 20,000 hertz, right? So if suppose a particular frequency is like very sensitive, then you may have like more biased, or like it's with that part of the cochleogram might be more sensitive. So it's like a subjective thing. But whereas spectrogram is like, like an objective thing. So it's not like, you like this frequency or anything. If that frequency is present, so that particular power will be highlighted. So more the power in that particular frequency at that particular time, more brighter will be. The thing like that. So now I hope this code is available with everyone. So can you guys all please run this code and see the spectrogram for like two different chirp signals. So chirp is something like the frequency changes with time. So here it's a linear chirp, which means frequency will linearly increase with time. So now if you see the spectrogram of this, you can see the spectrogram also shows this linear response. But for example, you take some other kind of chirp signal, which is like logarithmic. So it will increase in logarithmic. So not so rapid, but like in a logarithmic way. So then you can see similar such response even in the spectrogram. Can you guys all run this code and get this output? Then I can, like proceed further. If you have any doubts, you can ask. So just to explain, so here the things that we be having is like, so the libraries that we'll be having is NumPy and SciPy signal library, SciPy dot signal module to get chirp and also to compute spectrogram. So here like sampling frequency is like 44 kilohertz, and then like the duration of the signal will be like 0.3 seconds. And then we'll have like starting and ending frequency like 100 to 1000, which is like it'll start from 100 and it'll go like 1000. How a typical bird chirps. So we'll be creating two kinds of chirp signal. So starting is like, F0 and F1, but the method will be linear. So it scales up linearly like. But whereas in the other thing, it'll be like a logarithmic. So it'll have an like explosive increase. Initially it'll be slow and then it'll be like typical of logarithm. Then we calculate spectrogram using spectrogram function. So this SXX linear and SXX log will be like the two corresponding spectrogram plots, and you can simply use plot function to get these things. Has everyone got this thing? Anyone have any problem? Okay, so now let's go to this paper and appreciate the authors on what they have done. Okay, so it's like I hope professor also would have mentioned his talk. So what they have done is, so they have two kinds of task. One is a word recognition task and the another is a musical genre task. So as the name suggests, in the word recognition, there'll be like an utterance of word and the signals will be given. And you essentially calculate spectrogram of that signal and give it to the convolutional network. And it will say what word is been uttered. And in the musical genre, it's like there'll be a sample of music which will be, played and given as an input. And the corresponding spectrogram will be calculated. And the spectrogram image will be given to CNNs. So now what they have done is, so like when as we as humans, when we hear word or like any music, the cochlea is going to be the same. Only the difference happens in the deeper, the auditory cortex and things like that. So now can we have similar such architecture? So instead of two architectures, one for word and another for music, can I have something like this, like a branch like thing, where I have input, like similar to where and what pathway kind of thing. Like I'll have some common input layers, but then the network branches out into word recognizer and then music genre recognizer. So that's what they have done. So now they have also shown the accuracy versus the branching where it can occur. So if suppose the branching is like, happens at convolution 3, means 3 common convolution layers and then followed by branching, then the accuracy is like, very good. But if I have the branching at the fourth convolution or like have more shared layer and then branch at fourth convolution, then the accuracy drops very badly. So then we calculate the optimal point where we can have branching, which will be after convolution 3. So you have 3 convolution layers and have the branch. You can have a 2 also, 1 also. But why we didn't choose? Because if you have a convolution 3, we'll have lesser number of, like the lesser number of neurons. Because, if you have a convolution 2, then there's going to be 3 convolution layer in each, which will be like much bigger than having convolution up to shared convolution till 3. Then you may only need to have like 2 convolution layer at each branch. Okay. So, and again, like a typical thing, whatever we did this afternoon, like they showed how the first layer have these kind of features. And here, it's not just a visual feature, but instead it's a spectrotemporal feature. Why spectrotemporal? Because we have the frequency in the y-axis and time in the x-axis. So the feature that it learns will be a spectrotemporal filter. All right. So now this is where things get interesting. So now they also had a group of human participants and they did the same task in the humans as well. They had network which did the same task and also the human that did the same task. And they showed that how network and human performance were like very relatable. So they used a simple linear regression to calculate how one performance can explain the other performance, which is what linear regression does. So, and also they showed varying the different, the noise level in the background. So they varied the different noise levels and also the different, like, classes. And we can see both human recognition and network recognition are very similar. So this itself is a good observation because it says like although the network is very simple and like it has no biological underpinnings, but still it could able to perform very similar to what humans do. So now there is also one more interesting thing that they did. But before that, let's jump back to our code. Drop, please share. Okay. So which thing is like, so we have a code. It's a very simple code. What we have is like we generate data for word and then like music genre. It's a synthetic data. And then we assign some word and genre. And we have a shared branch network that they have proposed, like that they have shown in the paper. So we can see we have common features, which is like the common convolutions, which is like which has two convolution here. And then you have some word classifier branch and then genre classifier branch. So each of them have like two linear layers. And then we train this network. And then we can see like how uh, both using a single network that we can, like do both the task. So can you guys please run this and say like you could able to run this, and also we can go through this code. So now the code might be bit familiar to you because it's very similar to whatever the convolution network that we used before. Only changes like we have a common shared initial layers followed by a branch. Can you guys like quickly run it and see like you get some accuracy of both of them to be like around 90%, 9 or like 100%, and you could able to get this plot. If anyone have any problem, like they can put in the chat or unmute. I hope everyone is following this shift from vision to auditory that we did. And what is spectrogram? I mean, that is the whole part that, like you need to understand. All other things are like extra information. So how cochlea computes cochleogram, and then how a input signal is changed to some kind of image, and that image is like processed in the further area. So that's why you use a convolution, because ultimately all the signal is like, time varying, like 1D signal. The input to the convolution is going to be an image and how it is computed. I hope everyone is clear with that, because that's ultimately, like the crux of this paper itself. Okay, so I hope everyone got like good accuracy for both word and genre. Although the data itself is synthetic, because the actual data is like some 2 GB or something. So you don't want to like uh, take a lot of time in running and things like that. But I have also added the link for their original code. If you guys are like interested, like I'd also recommend to read this paper after this session, and then like check their own codes as well. Okay, so now the very recent, there are like so many works that people have done, and but why particular what is the particular reason that we chose this particular work to show is because they did something very cool, which is this particular.
Vigneshwaran, there is a question in the chat.
Oh, okay. Can you explain a bit on how? Yeah, okay. We'll see. So these are like the two different kinds of signals for two tasks. So usually what we do, like you train a network for one task, and for different task you train different network. But we know that that's not the case with our auditory or like visual thing. So what we have is like we have like a shared initial layers from cochlea to like some initial primary auditory cortex, and then the divergence happens like we saw in where pathway, what pathway. In that where pathway and what pathway also V1 V2 is like same. So can we have similar such architecture, and can we show that how the network behaves? When I say behaves, the accuracy for different groups of like different classes for both the task is very similar to how a human behaves. So that's what they have done. So they have network like this, and suppose let's take a particular like a word. Suppose, like Chetan. So now this particular word is like very well recognizable by both human as well as network. Now what they do on the x-axis, they add noise. So the ultimate clean one is like having the, of course, the maximum, like performance. But when we keep adding noise, we can see obviously it's someone calls you in a clean, like silent room and in some like big bazaar, it's obviously going to have some difference. It'll be much more difficult to recognize our name being called in a, like a noisy environment. So same way, network also, a network and human have this, like degraded performance with increasing noise. And all these different groups also are like having a similar pattern. Suppose this orange group, and orange group is like, having a same pattern in both network and human. Then the usual analysis is, can you predict a network output based on human input? So can I say what will be the, for example, human recognition performance at -3 SNR for a network using human. So which means I can, so that they are sure they can. So that's what it's, like the linear regression is about. So when you say linear regression is 0.92, which means the error is like only of 0.08. Like you can have a very good prediction of one using the other. Is it clear, the question? Okay, cool. So now, okay. So now so the final thing about this paper, like I said, like the very important thing is what they have did is, so now I can predict one behavior using the other behavior. Now can I go to a next level and can I predict the fMRI response using a network's output? So now it becomes a bit tricky. So I give some 165 sounds to both human participants as well as to the network. And then as a human hears, obviously there's going to be activation of different brain regions that you can effectively capture by fMRI. And fMRI gives a voxel response, and you get a particular region's voxel, particular ROI's voxel, and you get all this 165 sounds. And similarly, you give the same to the network, and you so for example, this feature map output. So this is the feature map for one. Uh, so this is the feature map for one sound, and similarly for 165, you get all these things. Now, can I predict this voxel response using this network's output? And they have shown they can. So now it becomes even more interesting. Why? Because the behavior matching is fine, but now even the layer by layer or like the layers output is also very similar to the brain's regions output. So that correlation is what makes it special. And they have trained using a linear regression. So you can see the voxel predicted or the voxel response predicted as some kind of linear relationship with respect to that some hidden layers output of the network. And they could show that the trained network could predict the voxel response much more accurately than some other random spectrotemporal or like some untrained network. So is this part clear to everyone? Because this is like the main theme of this paper. And so this is how like, the interdisciplinary neuroscience research, like propels forward. Is this clear with everyone, what they have done?
Yeah, hello, sir.
Yeah.
Sorry, my net went off somewhere. I couldn't get what you said. Can you like
Yeah,
repeat
sure.
it?
Yeah, so just stay unmute, so we'll have like conversation kind of thing.
Okay, sure.
Yeah, so we have network trained, okay, and we have human participants. Cool. So now I give some 165 sounds, like
Okay.
one by one, to both humans as well as to network.
Okay.
So now humans so whenever we hear a particular sound, obviously our brain regions are going to be activated.
Yeah.
So you can calculate using fMRI.
Yes.
So that fMRI values you take one particular region, for example, some like some temporal cortex, some part, and you get for all such 165 sounds. Okay.
Okay. Okay.
Then you give the same thing for network, and you get, for example, from convolution 3, whatever the feature map is there, you get all such 163 feature maps for
Okay.
all such. Now, using this feature maps, can I predict
Oh,
the fMRI output?
what the human have heard.
Yeah,
Uh-huh. That's nice.
yeah, that's what. So, and they have shown that you can predict.
Oh,
Okay.
okay. Fine.
Okay, so yes. So, and it's just a linear relation. It's not like, some very complicated non-linear relationship. Like you need some big network to train this itself for. It's a simple, like y equal to a of x kind of relation. And they have shown that it could able to predict. Okay, cool. So this is the and ask, could we get the coding material earlier for day 4? Then okay. There's no missing any sense. Yeah, so good question. So this is just for auditory. So you can check this group. So it's I forgot the lab name, but he's the professor. So the PA of the lab is Josh S. McDermott, and he has done similar work with the visual system also. So he again trained CNNs, and he again had some human responses, and he tried to predict and showed one like the relationship between both networks output and the humans, like fMRI response or things like that. So you guys can check out his lab page and recent works. So yeah, so now let's move on to our thing. So yeah, so this is the entire crux of this thing. And we have also like simply trained a branch network, and we had like two different class-based branches, and we could able to optimize for both the tasks. It's not like one branch is well trained and the other branch is not well trained. And the initial layers got mixed up between two, and it completely messed up like word recognition because of music. Nothing happened. It's like a clear hierarchy emerged where the initial layers tried some kind of, like edge detector in vision. Similarly, it did some very basic feature extractions. And then once that are done, then it aids the other two tasks. It becomes a more class specific to be quoting it in that way, like we saw in the MNIST data. So with this, I know we have time, but I think we are done. So I want to just say some points that are still actively pursued in the neuroscience research. So one example is the feature binding. So feature binding is, suppose let's say I am like seeing this particular picture, and there's a woman like petting a cat. So how my features that or like how my cat identified neurons are going to be binded with a woman identifying neurons? How are they both going to combine in such a way that in the further processing they both are like mixed for easier recognition? So that we still are not very clear. So there is a theoretical hypothesis called temporal tuning. So what temporal tuning is, it's like suppose this is assembly one neurons, like for example, cat, say, and like for example, the other is a woman. Yeah. So they both fire synchronously. So we can see they both fire in a very same amount of, in the same interval, in the maximum response to show the further layers that, hey, I see both women and a cat. So this still a theoretical thing, and there is like active research that's being pursued. So this is one such thing. And the other is, although we say convolution, like does this, but one important thing that we super simplify is, in real world, we actively see images as a video. We see it as a continuous stream of light. We don't see like a single image process and then says what is it. So our filter should not be just, spatial filter like edge detector or like, some horizontal line detector. It should be rather something called spectrotemporal filter, which is like both time as well as space should be the axis of our filter. That we are like missing it. I think tomorrow or like I think tomorrow there will be a session on deep oscillating neural networks where I think they will show you about a concept called temporal tuning and how such a network is essential to capture such spectrotemporal like spatiotemporal feature, not just a spatial feature that we have seen so far in convolution. Okay, so I hope this is clear. Uh, and also I'll just ask one question for you guys. Uh, Suppose you are looking at your monitor and like actively listening. So in our eye, we have two kinds of, in our retina, we have two kinds of photoreceptors. One is called rods and other is called cones. So cones are in the central part of the retina and they are the one which are color sensitive. So we can see color because of only those photoreceptors. And the other which lies in the periphery, let's open. The one that lies in the periphery is not color based, but rather, like, yeah, so, yeah, this is better. So, yeah, so there are rods and cones. So rods, you can see they are in the, like, in the periphery, and they are used for detecting, for example, they are very high light sensitive. Suppose you see a rat running, in your room suddenly. So you don't pick that using our cones per se. You'll be using rods because they are like fast firing neurons, and but they are colorless. Okay. So now the question is, you are seeing a image, and you see it using both rods and cones, and whatever you see straight are going to be seen by cones, which are color sensitive. But you don't see the black and white image on the periphery. You see only color everywhere. So can anyone say how is that possible? Is my question clear? I'm like,
Yes, so I think because the processing speed is also very fast and our brain fills up the information. So we don't see one thing at one point in time. We also skim through everything. And whenever we see in one particular space, we see colors, and then when we move to the next one, the color from the previous scene does not go away. It retains, our brain retains it
yes,
for.
exactly. So now to put it in a different thing, can I say, uh let's take
Yeah, but
some image.
basically, we don't, the color is perceived in our brain, right? What we see is black and white only, right?
No, although it's perceived at different levels, but the
Mm.
actual color coding happens in the retina itself. It's not like we don't know color information till it goes to the brain.
Oh, okay. Right.
Okay. So now let's take one image. So yeah, so as she said, that's what exactly. Now to make it, so let's say you are in some vacation and you see this as your view. So now your you see some image something similar to this, and obviously where the cones are, that's where you'll have a high resolution, and all these other might be bit blurred. The resolution is going to be less, but they are colorful. It's not like they are black and white. So now to say whatever she said in a different term, it's like all these part of image that you see, it's not the live image you see. It's like some t minus some time that you have seen, and it's simply the images like stitching together so that you see it as a one color image. So is it clear? Like,
Yeah, the image is already processed. What we see is not exactly what's happening. That's what you're
Yeah,
commenting.
exactly. So it's like if you see this, you think you are seeing the image as t equal to 1. But actually, this part of the image, you have actually seen a t equal to like some minus
It's
3.
pre-processed already.
Exactly.
Yeah, I read this somewhere. Like I don't know if this is off topic, but I read somewhere that it takes at least zero point 0.5 seconds from our brain to do something. So in reality, we are basically time traveling.
Yes. Yeah,
Uh,
exactly. So, yeah. So when I heard it, like it was really spooky for me. But yeah, so I just want to share that before. So
it's
yeah,
very
so
cool.
that's why spatiotemporal filtering is like very important because that's how actual neurons work. But although we could match very much many observations that we have in brain, but to go in the real direction, it should be a spatiotemporal filter. So, and some more hard problem that people like in vision currently they do is something called painting. So all this, so you see an image like this, but you have some, how do you know that, for example, this boundary or this boundary that surrounds the girl is different from the background or like this guy? So again, so that's what is called like that's what the artificial intelligence people call this problem as painting. Suppose I want to insert this guy without messing up any of the background. Even if he crosses this girl from the background, it should not mess up the the image of the girl. So how do you do that? So again, it's all these things I'm like mentioning so that these are the problems like the active like the research side like being pursued. And yeah, so I guess that's it. Time. Yeah, I think it should be fine. I hope the session was useful, at least like bit useful for everyone, and it created an interest like how the field is fascinating and like actively like rapidly changing, and how like different interdisciplinary things are coming together to explain like one system. I hope it will be a good opportunity for everyone to appreciate it and like it's cool. If you have any questions or something like you can mail me that I have mentioned in the code book. And yeah, hope and that's end of day 2. Aditya,
Yeah.
cool. And Sundari will share you the quiz for you guys. Maybe in half an hour.